Да, давайте начнем. Собственно, я буду свои лекции вести по-английски. So, I'm going to talk about I'm going to talk about Lüroth's theorem on field extensions. First of all, let me state some plan. So I divided my lectures into 3 parts. So the first part is the theorem itself and its proof. The second part will be some discussion about applications of this theorem. To some rationality problems. And the third part, which is actually the main part of my lectures, is an application of this theorem to a theorem of Knop. About reductive group actions. So I'm not going to state the theorem now, so you'll see. Okay, now let me proceed to the first part. So what is this theorem about? So this is actually about field extensions. So what do we have? So suppose K is a field. So let's take a field. I put no restrictions on it. So any. For the moment, for this theorem, the field may be any. Not necessarily algebraically closed, not necessarily of characteristic 0. So it may have positive characteristics. So now consider a purely transcendental extension of this P field of some degree. So purely transcendental of degree n. So we just add n algebraically independent variables. Okay. Now I can state Lüroth's problem first of all. Lüroth's problem. What is it about? So we have K and its extension this. Now consider any intermediate subfield. So let L be a field such that K is contained in L and L is contained in this purely transcendental extension. And the question, is L also purely transcendental? So is it clear? So this is the problem. And now I'm going to survey some results, some known results in this problem. So in general, the question, the answer to this question is no. But in some particular cases, it is yes. And Luroth's theorem is about the case where n is 1. So n is 1. And in this case, the answer is yes. And this is exactly Luroth's theorem. So this was proved by Luroth in the 19th century. There is also a positive result for n equal to 2. So let me write yes if the characteristic of our field is 0. And this is known as Castellnuovo so this is not the Luroth's fault. And for higher values, so let's say n starting from 3, the answer is no. And actually, you can see a gap in time. So this is known since only 1971. So you can see a huge gap in time. So this for many years this was an open problem.
And for n equal to a positive characteristic, the answer is also.
In this case, in positive characteristics, there are counterexamples, but so these counterexamples are related to separability conditions for positive characteristics. So if you require in addition some separability condition, then in this case this will be also true.
If k is perfect,
I guess yes. Okay, so today I'm going to prove Luroth's theorem. So it has a rather elementary proof, and I'm going to provide it. So let me probably here state the theorem. So Luroth theorem. Suppose we have a chain of fields. So we take a purely transcendental extension of k by one variable. So suppose f is strictly greater than k, then there is an element alpha, which is in f but not in k, such that f is generated by alpha over k. So is it clear? Okay. I need to make some preparations.
And alpha is transcendental over k.
Alpha is transcendental. Yes, I'm actually going to prove it now. So if you take so what is k of x? This is just the field of rational So these are, so its elements are just quotients of polynomials. So let's take any rational fraction, beta. Then, by definition, it can be represented as a fraction. So f divided by g, where f and g are polynomials, and g is of course non-zero. And we may also assume that the fraction is irreducible, so f and g are coprime. So GCD of f and g is 1. In this case, we can define the degree of beta. So the degree of beta so this will be the maximum of degrees of f and of g. Yeah, so for every polynomial we have this notion of degree, and so we extend it to also to all fractions, just by taking the maximum degree among the degrees of the numerator and denominator. Okay. Now lemma. Now lemma. So let's take an element which is not a constant. So it has some degree, which is positive in this case. Then there are two claims. The first one is that beta is always transcendental over k. And the second one is about, we can add this beta to k, so generate a subfield, and compare this subfield with k of x. So consider this extension, and I claim that this extension is finite and has degree n. So let me write it as algebraic extension of degree n. So, is it okay? Okay. Now let's prove it. So, how we do it? We again express beta in this form as above, right? We can write explicitly f and g as polynomials. So let n be the degree of beta. Sorry, we already know it. So let's write f is an. So express f as a polynomial, express g as a polynomial, So recall that n is the maximum of the degrees. So I claim that at least one of these coefficients is non-zero. So probably one of them could be zero. But for me, it's just a convenient way of writing. Okay. So we take this fraction, and now AI, BI, these are all elements of K, right? And then we have, so beta is F over G, and so we have F minus beta G is 0. Right? So we can rewrite it as an minus beta en x to the power n, a1 minus beta b1 x plus a0 minus beta b0. And so this is equal to 0. Right? So when we look at this expression, you see that this is an algebraic relation on x with coefficients in k of beta. Right? So first of all, I would like to show that this relation is non-trivial. So if AI minus beta BI for any I, then we know that the polynomial G is non-zero, so it has at least one non-zero coefficient. For I with beta I non-zero, we have, what we get, beta is AI modulo BI, but this is just a constant. It belongs to the field. Which is impossible because we have this assumption that, which assumption? So beta is not a constant. Contradiction. So there is I such that AI minus beta BI is non-zero. This means that the relation is non-trivial and X is algebraic. So X is algebraic over this field, K of beta. Is it clear? So, okay. We can write that X is algebraic over this bigger field, K of beta. Yeah. So now we need to prove the first part and also that the degree of this extension is exactly n. So we have this chain of extensions, field extensions, and now we know that this one is algebraic, right? So if this extension were also algebraic, then we would have that the composition of extensions would be also algebraic, which is not the case. So this means that this extension is transcendental. So, and we have actually proved the first part. So this is easy. And now the last point which remains to be proved is the claim that the degree is exactly n. Actually, we are going to prove that that this is a minimal polynomial, so this is irreducible. So we will show that this polynomial is irreducible.
In this statement, I think we should require that n is positive.
Yes, we require it. So we take beta not belonging, so not non-constant. This means that actually, so I can go so n greater than 0, right? So okay, I write again this polynomial an minus beta en x to the power n plus a1 minus beta b1 x plus a0 minus b0. And now this polynomial is regarded as a polynomial. Actually, so I want to, let me change the variable. So this will be just a polynomial in another variable, different from x. So let's say it's z. So this is a polynomial in the variable z with coefficients in our field k of beta. Right? And I'm going to prove that this polynomial is irreducible. Okay. Assume b is expressed as a product of two polynomials, where both of them are still polynomials in the variable z over this field, but the degrees are strictly less than n. Yes? Now, we can actually notice that this polynomial, so the coefficients of this polynomial are not actually elements of this field. They are elements of the corresponding ring of polynomials. So they all have no denominators. Moreover, all these polynomials, they have degree 1 in beta. So is it clear? Okay. So we actually have P. So this is a polynomial. So I can write it like this. But now I claim that if you have such a polynomial, and if we express it as a product of two polynomials with coefficients in the field, we can actually multiply. So there are actually, so we can actually get rid of the denominators. So this means that P1 and P2 may be chosen, can be chosen. To lie in I think there is a standard fact from algebra, so something like Gaussian lemma. Okay. In this way, so let's recall that f is actually so p is actually f f of z minus beta g of z. So from the definition. And it has degree 1 in beta. Right? So this means, so look, we have a polynomial which has degree 1 in beta, and this polynomial is expressed as a product of two other polynomials. And now I claim that one of them should have degree 0 with respect to z. With respect to beta. So the degree of p with respect to z is 1. This means that among these two polynomials, exactly one has degree 1 and exactly one has, so the other one has degree 0. So
degree with respect to beta.
Sorry, yeah. With respect to beta, right? Okay. So we may assume that the degree of P1 with respect to beta is 0, and the second one is a polynomial depending only on z. Then we can, so this one has degree 1, so we can write it just P1 is F1 minus beta G1, so for convenience, where F1 and G1 are polynomials in Z. And in this case, we can just multiply. So this one we multiply by P2. What do we get? P, which is F minus beta G. This is equal to P1, P2. And we can multiply F1 P2 minus beta G1 P2. Right? So what do we get? This means that F is F1 times P2, G is G1 times also P2. So what is the contradiction? Yeah. So this means that we have found a common factor, which means that F and G are not actually coprime. Contradiction. Contradiction. It's S, so these two polynomials are coprime. Sorry?
It can be a non-zero constant.
It cannot be non-zero constant because it has degree 1. Sorry, P2.
P1
P2.
is just a polynomial.
We assume that there is some logical composition of P is equal to 1 and 2.
Yes. So let's say here we are talking about the degree with respect to Z. The degree with respect to Z. And this is strictly less than n.
It's strictly greater than 0.
And as a consequence, it is strictly greater than 0. Right. So this is a good question. Okay, so I claim that we have proved that. So conclusion. P is irreducible. So this is a minimum polynomial of x over this intermediate field K. This means that so the degree of this extension is exactly which completes the proof of this lemma. Are there any questions at this point? So let me also deduce some straightforward consequences of this lemma. So probably, so it's a good point to copy this lemma here. So, lemma. Of degree n. Corollary. So let me mention two parts. So now assume that k of beta coincides with k of x. What does this mean? So when is it possible? So this is, this is exactly the condition that n equal to 1. And the second part, so as a consequence actually of the first one. So we can describe all the automorphisms of this field over K. So these are going to, these are described as expressions like this, where A, B, C, D are some constants, and AD minus BC is 0. So because any automorphism is uniquely determined by the image of X, and from the first part we see that this image should have degree 1. Okay. let's proceed to the proof of the theorem itself. So proof of Lüroth's theorem. So we have such an extension, and we need to prove that it is generated by a single element. So let's take beta. So we know that f is strictly greater than k. So we can take any element which is not in k. From the lemma, we know that k of x is algebraic over k of beta. This means that k of x is algebraic over the bigger field f. Right. Okay. And now consider the minimal polynomial of x over f. So let's denote it like a1z plus a0. So this is a polynomial with coefficients in f. So this will be the minimum polynomial. Of x over f. Okay. All the coefficients belong to f, but still they are fractions of, still they are quotients of two polynomials with coefficients in k. So actually we can get rid of all the denominators and obtain another polynomial with coefficients which are polynomials in k. Polynomials with coefficients in f, in k, sorry. So we can write ai, these are elements of f, which are actually fractions, so quotients of two polynomials. Multiplying by the common denominator, obtain a polynomial h. This will be bn zn plus bn minus 1 zn minus 1 plus b1z plus b0, where all the coefficients bi are just polynomials. Next. And we may also assume that they have no common multiples. So the greatest common divisor of all of them is 1. Right? So we started from a polynomial with coefficients in f, and modified it into a polynomial with coefficients which are polynomials in k. No, with coefficients in k. Sorry.
But probably not from f.
Not from f anymore. Right. So what is the main property? So all the coefficients are polynomials in the variable x with coefficients in k, right? And if we substitute z equal to x we get 0.
So z equal to x, this will be 0.
Okay. Now, we know that n is the degree of h with respect to z, right? We can also consider the degree of this polynomial with respect to x. So let's denote it by m. The degree of this polynomial with respect to x. Okay? And now, the next thing. X is not algebraic over K. So we know this. Right? Therefore, there exists at least one of these coefficients here should not lie in K, such that AI belongs to F but not in K. Right? Moreover, let me write it. Note that the degree of AI doesn't exceed n, because AI is the quotient of the corresponding coefficients in the second polynomial, right? And all of them have degree not greater than m. So next, are you still with me? It's a bit technical, you see, right? But, so in my opinion, it's still rather elementary. What is the next step? I claim that this AI is the desired generator of F over...
So it will be dx, right?
Sorry?
Dx. AI was controlled, now we have transferred everything to dx. So the last...
So this one is the quotient of some, so actually... AI is equal to bi divided by bn, right? So each of these components has degree at most n. Therefore, the degree of AI itself is also...
So you've gone back to H0.
Sorry?
You've gone back to H0.
Yes. Yeah. And I claim, so consider this AI. I claim that this element is the desired alpha, as in theory. You see? So here is how we get this alpha. And now, of course, we should prove that that alpha generates the extension F. Okay. We can write it as, again, as a quotient, F mod G. So both of these, both of the polynomials have coefficients in K. We may also assume that G is not 0, and they are mutually, so they are coprime. Let me also notice that the degree of f doesn't exceed m, and the same for the degree of g. Right? So, consider polynomial P0, which is f of z minus alpha g of z. This is a polynomial in variable z with coefficients in f. Now, we know that so if we substitute x, so what do you get? So if we substitute z as x, so this will be, let's see, where is it? Let me write it here. So alpha is f. Sorry? So yes, this is a root. So this is just by definition of alpha, we have this 0. So we have a polynomial which has x as its root, one of its roots. And also we have a minimum polynomial for this x. So what does this mean? This means that the polynomial P0 is actually divisible by H0 in the ring f of z. And so we can write P0 is Q0, H0 for some Q0 polynomial in f of z. Right? Now, again, I would like to get rid of the denominators here. So I can rewrite P0 as f of z minus g of x, f of x, g of z, divided by g of x. Right? So this is a, so we have this extension expression by the definition. And also recall that we can multiply h0 by the common denominator to get h. Right? So this means that actually we can express this polynomial. So getting rid of the denominators, we can express this polynomial here as a product of some q and h, where q is some polynomial with coefficients in k and z. So again, we have such an expression for elements, for polynomials with coefficients in f. All the coefficients in f are fractions of x. But getting rid of the denominators, we can obtain a similar expression for, so with coefficients which are polynomials in k, polynomials, not fractions.
what's happened in the previous slide?
This one.
Yes.
I have just expressed P0 by definition. So P0 is this. And we also substitute alpha as f of x modulo g of x. And just rewrite this. Yeah? Is it clear? Okay. Now let's count some degrees. So what about, so what is h? H, this is a polynomial here, written here, right? What about the degrees? The degree of, so this will be p, yeah? The degree of p with respect to x. So what can we say about it? This is bounded by L, right? Because m is the maximum, so m is the bound of the degrees of f and g, right? But what about the degree of the right-hand side with respect to x? So what do we know about this?
It is not less than m.
Yes, it is exactly m.
Sorry, it's written here actually.
Yes, yes.
What does this mean? So how can this happen? So the degree of h is m, then we multiply it by something and get a polynomial whose degree with respect to s is not greater than m. So this means that actually q doesn't depend on x. Q doesn't depend on x. So q, this is actually a polynomial purely in the variable, only in the variable z. It doesn't depend on x, right? I actually claim that this q is a constant. So this is a scalar. So why is this? Let's look again at this equation. So on the left-hand side, we have some polynomial in x and z. On the right-hand side, we have a polynomial which is divisible by q. So assume that the degree of q is positive. Yeah? And now again, look at this expression. So let's take R1, the remainder of f of z modulo q, right? R2, the same for g of z modulo q. Right? So replacing each of these polynomials, so f of z and g of z with their remainders, we still get an expression which is divisible by q. So is it clear? So R1 of z, g of x minus f of x, R2 of z is actually divisible by q. But what about the degrees? So the degree of this expression with respect to z is strictly less than that of Q, right? Because this is formed by remainders. Now we can conclude that actually this expression is 0. So what does this mean? If R2 non-zero, then so we can divide. We get f of x over g of x. This is equal to r1 of z, r2 of z, right? So you see that the expression on the left-hand side, it depends on x. And while the expression on the right-hand side, it depends on z. So how can this happen? Only if this is a constant, right? But this one is actually alpha, and alpha is not a constant. So this is alpha so on the one hand it is alpha, on the other hand it should be a constant. So how to write it? Okay, alpha contradiction. So it's impossible. Okay. So this was the case R2 is non-zero, so we have shown that this case is impossible. So R2 is 0, which means that R1 is also 0. So this means that both f and g are divisible by some polynomial of positive degree, and they are not coprime. F and g are not coprime. So we again obtain a contradiction. So what was the assumption? So here is the assumption, right? We conclude that Q is actually a constant. So this is an element of K. Yeah. F of z g of x minus f of x g of z is equal to Q times h, where Q is a constant. Right? Now, So I think I actually need only a few minutes to finish the proofs because we are close to the end. So let's look at the degree of h with respect to x. This is m, right? So h is equal to this polynomial, right? Do you see that actually it is symmetric with respect to the interchange of x and z? This means that the degree of this polynomial with respect to z will be the same. Because of the symmetry. But this one is n. So the degree of h with respect to z is n. Okay? So this means that the maximum of the degrees of f and g is n, actually. Yes. In turn, this means that alpha has degree n. Alpha has degree n. Now, consider the chain of extensions. So we have this extension, right? This chain of extensions. But what do we know? What do we know? We know that the extension degree of k of x over f is n. So this was from the very beginning. So n was the degree of the minimal polynomial of x with respect to over the field f. At the same time, the degree of k of x over k of alpha is also n.
According to lemma.
According to the lemma. So, how can it be possible? We conclude that actually the extension degree of f over k of alpha is 1. And so k of alpha coincides with f. And this is the end of the proof. And so I think this is a good point to finish for today.